Hey everyone, welcome to the second video on chapter 3 of Designing Data Intensive Applications book. In the last video, we talked about append-only logs and how hash indexes can be used as an indexing structure with them. In this video, we'll see what SSTables and LSM trees are and how they can overcome the limitations of hash indexes. Now, in case of append-only logs, we saw that each log structure storage segment that we had was a sequence of key-value pairs. So also these pairs appeared in the order that they were written. So the values which are later in the log, they takes precedence over all the values which we have for the same keys earlier in the log. Now in this case, we can make a simple change to the format of our segment files that we have. So we require that all the sequence of key value pairs that is being written in the log file is sorted by key. Now this new format is called a sorted string table or SSTable for short. So at first glance, it looks like that this requirement to store the keys in a sorted order, it breaks our ability to use the sequential writes into the log. But we'll get to that briefly in a moment. So in this diagram on the left, you can see that all the keys that we have in this log file, for example, handbag, handful, and handkerchief, they're all stored in a sorted way. Now this simple property of SSTables, they provide us with several big advantages over log segments, which we use with hash indexes. Now let's take a look at some of the advantages here for SSTables. So the first one is that merging the segment files in case of an SSTable is very simple and efficient. And that works even if the files are bigger than the available memory that we have. So this is because the approach that is used for merging here in this case, it's the same that is also used in the merge sort algorithm. So let me explain that with an example here. So in case of merging these segments, you first start reading the two input files side by side. So in this case, we have these two segment files, segment 1 and segment 2, and then we'll look at the first key in each file. So for segment 1, the first key is handbag, and for the segment 2, the first key is handcuffs. Now we'll copy the lowest key according to the sorted order to the output file. So the output file that we have in this case is the merge segment. So out of these two keys, the smaller one is the handbag. So that's why it's written first to the merge segment. And then the pointer is moved to the next key. So in this case, so this compaction and merging process, it will give us a new merge segment, which also will be sorted by key. So, and we already saw this in the previous video that the compaction and merging process, it already takes care of removing all the duplicate entries for us. Now let's look at another advantage of SSTable and how they help us in finding a key in the log file. So finding a key is also very efficient in case of SSTable. So if you have to find a particular key in the file, then in this case, you no longer have to keep an index of all the keys in the memory, like we did with the hash indexes. So let's also say this with an example. So now in this case, let's see, we want to search for this key and value. Sorry, we want to search for this key handiwork, and this has a value of 45521. So now let's say we also don't know the exact offset of this key in a segment file, but we do know the offset for these two keys, handbag and handsome. So the offset of these two keys are 102134 and 144667. Now because of the sorting property, we know that the handiwork key, it must appear between handbag and the handsome keys. So this means that you can just directly jump to the offset for handbag, which is 12134, and then you can scan from there until you find the required key, which is handiwork. So in this case, we saw that we don't, so we still need an in-memory index, like to tell you the offset for some of the keys, but this hash map can be a sparse index. So you don't have to keep all the keys in the hash map. So this property, it greatly reduces the memory which is required to store the hash indexes. Now, another advantage of SSTables is how the segment files are stored on disk. So we saw in the previous slide that we need to scan over several key value pairs in case we get a read request. So it's also possible to group those records into a block and then compress it before writing to a disk. So in this case, this whole area is a compressible block. So this whole block can be compressed before this is written to a disk. Now this is also because each entry of the sparse in-memory index that we have, it points to the start of a compressed block. So in this case, handbag is pointing to this compressed block that we have that's shown in red. And in case, and this, the handsome, which is another key in this in-memory hash map, it's pointing to a different compressible block. So besides saving disk space, because we are using compression, it also reduces the IO bandwidth that will be used. So it all looks so good so far, but let's see, like, how do you get your data to be sorted by key in the first place? Because we saw that all our incoming writes, it can occur in any order. So there are plenty of well-known tree data structures that we can use for this. So there are red-black trees, there are also AVL trees. So with these data structures, we can insert the keys in any order in the tree and then read them back in the sorted order. So this is how our storage engine will work with these data structures. So let's say when you have a write coming in, then you can add it to an in-memory tree data structure, for example, a red black tree or an AVL tree. So this in-memory tree is also called a mem table. Now, when the mem table it gets bigger than the threshold, typically let's say if it reaches a few megabytes in size, then you write it out to a disk as an SSTable file. So now this can be done very efficiently because the tree already maintains the key value pair sorted by key. So the new SSTable file that you have, it becomes the most recent segment of the database. So also let's say when your SSTable it's being written out to disk, then all the new writes that you are getting in that case, it can continue to a new memtable instance that you have. So yeah, we saw how we can construct an SSTable. Now let's see how to serve a read request from that SSTable. Now in order to serve a read request, so first what you need to do is you have to try to find the key in the mem table that you have in memory. Then you will go to the most recent on this segment, then to the next older segment and so on. So it's the same process that we saw in case of hash indexes. So also from time to time, the system will be running a merging and compaction process in the background. So that will combine the segment files together, and it will also discard all the overwritten values or the deleted values, which were being deleted using the tombstone record. So one problem with mem tables is that let's say if the database crashes, the most recent write that you have. So all the recent writes will first since go into the mem table and then they are being written to the disk. So in this case, all the recent writes that you have, which are still in memory, those will be lost. So in order to avoid that problem, we can keep a separate log on disk. It's called a write ahead log. So to that write ahead log, you will append every writes that you are getting for the DB. So that log it won't be in a sorted order, but it won't matter for us because the only purpose of the write ahead log is to restore the in-memory table, the mem table that we have after a crash. So let's say, and also like let's say every time the mem table is written out to an SS table on disk, the corresponding write ahead log that you have, you can just discard that. So we have talked like all about SS tables. Now, what are LSM trees? So there are some storage engines that are based on the principles of the merging and compaction of the sorted files using SSTables that we just saw. Now all these storage engines are often called LSM storage engines. So LSM stands for log structured merge trees. So that's how this terminology of LSM trees comes into picture. So similar LSM storage engines, they are also used in the Cassandra DB and also HBase. So in both of these, they were inspired by Google's Big Table paper. So it was actually Google's Big Table paper which introduced both of these terms, SSTables and memtable. Now another issue with SSTables or the LSM tree algorithm that we have is that it can be really slow. Let's say you want to look up a key which does not exist in the database. Now in that case, what you have to do is you have to check the memtable first because that's in memory. And then you have to check all the segments like all the way back to the oldest before you can be sure that, okay, this kit does not exist in the DB. So now this process can be really time consuming. So if you have to optimize this kind of access, So storage engines often use an additional data structure. It's called Bloom filters. So Bloom filters is not scope of this book. So I'll just go briefly over what a Bloom filter is. So it's kind of a probabilistic data structure which is used for approximating the contents of a set. So it can tell you if a key does not appear in the database, and it will save you many unnecessary disks for, let's say, in the case when you are trying to find keys which are non-existent. So one property of Bloom filter is that like they have a non-zero probability of returning a false positive. So it means that it can also report that an element is a member of the set even when if it's not. However, like what works in our case is that they have a zero probability of returning a false negative. So what it means that if a Bloom filter reports that an element is not a member of the set, so it's definitely not going to be a member. So this is how Bloom filters can save us many unnecessary lookups for non-existent keys. So LSM trees continue to work well even when the dataset that we have is bigger than the available memory. So since the data is stored in the sorted order, then we can very efficiently perform the range queries also. We don't have to go and scan for all the keys like we were doing in case of hash index with append only lock where we were storing all the keys in the hash map. So also the LSM trees, in this case the writes are still sequential, so they can still support remarkably high write throughput. So this was all about SSTables and LSM trees. In the next video we'll talk about using B trees and how they can be used as an indexing structure for the databases.